Thanks everybody for coming, and thanks for sticking around for the whole session. So we're almost there, and then we'll chat afterwards. I'm going to talk a bit about music and the aging auditory brain. So it should be no surprise to anybody that as you get older, your hearing gets worse. Actually, hearing loss in age is pretty much the most common health issue reported by older adults. Not as severe as cancer, things like that, where you're going to die, but it does have lots of effects. So not being able to hear, having difficulty with hearing, can lead to things like social isolation. You can't understand what your friends are saying, can't have a conversation with them. This can lead to things like depression. And there's even some research now that shows that even mild hearing loss in sort of late middle age can predict cognitive decline. So finding ways to improve hearing is really about most importance. Maybe if we can catch cognitive decline early, kind of like what Kartik was talking about, before it starts to manifest, then we can help people earlier on. And so hearing might be that signal. So I run something called the Cognitive Aging and Auditory Neuroscience Laboratory, or CANLab, and we're interested in three broad types of questions. How does the brain process sound, especially music and speech? How does auditory processing change with age? And how does other forms of training or musical training impact hearing abilities? And again, our goal is to find ways to improve hearing by understanding these mechanisms more. Now, if you talk to an older adult and say, you're having trouble with your hearing, what are they going to say? Well, usually in an environment like this, where there's just one person talking, it's relatively quiet, it's actually not that problematic. The problem emerges when you're in a noisy environment, like a coffee shop, a bar, driving a car, or working on a construction site. It's that noise that makes it difficult to understand. And the reason is because hearing is not just your ears. Hearing is your brain, and we call this auditory scene analysis. And when you think about it, an auditory scene is made up of lots of sounds. So you can imagine you're at a coffee shop, there's somebody playing guitar, you're trying to chat with somebody, there's some construction noise outside. Now, all those sounds actually reach your ear at the same time. So you just have a little flap of skin in the eardrum. All those sounds are moving the eardrum together, and then they all hit your brain as one combined noisy signal. And your brain has to separate those, has to break that apart so you can actually perceive the guitar playing, the person talking, and the construction noise. So hearing is a brain problem, and your brain is really the most important part of the auditory system. To study the brain, we use EEG. I think a lot of people have talked about this, so I'll go through this quickly, but your brain is made up of billions and billions of neurons, and when they activate, they produce a very small electrical current that you can measure on the surface of the scalp with an EEG sensor. And that's what we measure. This is what a cap looks like. So we put sensors onto the cap, we attach it, put a person in a room, and I think enough people have talked about this so far. This is what EEG looks like. It's just a bunch of squiggly lines, and very little information is actually apparent on this screen. It just looks like waves. So we can analyze it in lots of different ways. And we use a lot of these techniques in my lab. So one way to analyze it is to look at how fast the waves are coming in. So we can look at, are you having very, very fast waves, very slow waves? If you've heard of like alpha waves or beta waves or gamma waves, things like that, that's what we're talking about. Here's the frequency of the waves, how often they're occurring. We can also use source analysis techniques. There's ways to sort of figure out where in the brain things are coming from. These are not great with EEG because, again, we're measuring the surface of the scalp and trying to figure out where things are coming from, but we can estimate and get some ideas. One of the most common techniques I use is called the event-related potential technique. And what we do here is we present the same type of stimulus multiple times. So we'll present a sound over and over and over again, and then average it together. And that gives us a signal that looks like this. And then we can actually measure those peaks and talk about how large they are or when they're occurring. And then the last one is, I just want to talk about this because it's a brand new technique we got in the lab. And it uses this ERP technique, but we're now able to get really, really clean signals. And we can actually hear a person's brainwaves. So I'm going to play a sound. I hope that's very quiet. I turn this up. Try it again. Very quiet. I apologize. Sounds are not coming through loud. Anyway, we can hear people's brainwaves. We'll have to do that after. And so how can we improve hearing by understanding the brain? Well, the brain is a plastic organ. It can reorganize itself based on its experience. So we can potentially use training to help reorganize the brain. How can we do that? Well, one natural example would be to look at musicians. They spend a lot of time thinking about sound. We can compare them to non-musicians. We can also give people musical training and see how they do before and after with their hearing abilities. We can also use other areas of cognitive strength to potentially scaffold the development of hearing. And I'll explain what I mean by this in a little bit. But we can look at areas of potential cognitive strength and maybe music perception. Older adults don't show decline in wanting to listen to music. So maybe music perception is an area of cognitive strength that we can use. I'm going to talk a little bit about all of these, and these are all topics my lab has explored. So first I'll talk a little bit about musicians and non-musicians. And what I put here is a graph. All that's important here is that the graph shows age, and better hearing in this case is down. And this is a performance on a speech and noise test. So we ask people we present a sentence to people and ask people to repeat it to us. And it starts out very easy. Of course, it's going to be too quiet. And then we make background noise louder. I'm not sure if I can have this. Oh, is it on the desk? There we go. Let's try that. A little louder. All right. Let's try that one more time. So pretty easy. Anybody can repeat that aloud to me? Good. All right, now we can add background noise to that. Everybody hear that one? No, it's a bad speaker, and then we can make it really hard. Very hard to understand. The sentence was a square peg will settle in the round hole. The important thing here is that as we get older, the ability to do that task gets worse. What's really interesting is when we look at groups of musicians and non-musicians, we see that rate of decline is actually much lower in musicians. So much so that the average 70-year-old musician is doing this task as well as the average 50-year-old non-musician. So that's a huge amount of benefit from musical training. But there's a problem with that, is that maybe by comparing musicians and non-musicians, we're just comparing people who had better hearing to begin with. And that makes sense. Maybe with good hearing, you're more likely to become a musician than if you have really bad hearing. So the way to overcome that is to actually provide training to people and give people piano training who have never had music lessons before and see if they get better at hearing abilities afterwards. And we did this. So here's one of our participants. We brought pianists to their home, computers, set them up, and it was a self-directed program, kind of like Guitar Hero or Rock Band. Here's her with her very first time touching a piano, and the goal here is to tap one note in time with the metronome. So it's her first time touching the piano, and she has a long way to go. But we came back 6 months later. Oops. Came back 6 months later, and most of this she did on her own. This is on her own, and then she's improved. So pretty dramatic improvement over 6 months. She did it herself. She's much happier this time. But the real question from our perspective is, did it change her ability to understand speech, particularly in background noise? And we did a lot of studies on these people because we invested a lot of time giving them piano lessons over the course of 6 months. So we gave them a couple of speech and noise tasks. We looked at their brain activity using EEG, and we looked at ERPs. We also did an MRI task and looked at their brains using MRI. I'm going to sort of go right into the behavior again. Here's a graph. What we did in this task was gave people a word, one word presented in background noise, asked them to repeat it out loud, and then repeated the task over and over again. And what we have here are 3 different groups. We had a music training group, and then we had a no contact group over here, so they did nothing. And then a video game training group, which was like our placebo. And I'm not going to talk too much about that, but if you want to ask questions about it, I'll be over there. The different colored bars represent the session. So blue is before they started, green was about halfway through, and orange is the post training. And you can see the music training group improved their accuracy about 10% over the course of training. The other groups showed no difference at all over the course of the training. So we can now say that music training improves the ability to understand speech in noisy environments. What was interesting, though, is we looked then at the brain areas involved using both MRI and some of the EEG source analysis techniques. And we found two types of regions that were involved in that showed change as a function of the music training. One was regions related to auditory processing, which was not a huge surprise. We kind of expected that. The region that we were surprised with was we found regions involved in motor planning. And in one of those tasks, there was no motor task. They actually had to press a button to select what they had heard, not say it out loud. But why is a motor system being enhanced by music training? And we dug into literature a bit and realized, oh, the auditory system actually uses the motor system to hear. So when you are and especially when it's noisy. So when you're having trouble listening to somebody, your brain actually tries to figure out what are their lips doing? How could I reverse engineer this sound? How would I move my larynx to make that sound? How would I move my lips? So your brain sort of sounds it out automatically. And so we saw this motor and premotor system engage, and then we thought, well, piano training, what's it doing? You're learning to connect finger movements to sound. So music training might connect that auditory and motor system, and that provides a benefit to understanding speech and noise because understanding speech also relies on the motor system. So music training improves hearing abilities. So I'm going to switch now and talk a little bit about music perception in older adults. So if we think about what we know about cognition as we get older, there's a lot of normative changes that happen. Some things get better, so things like crystallized knowledge tend to improve as we get older. Being able to see big picture things improve as we get older, but some things get worse. We usually do worse on things that require very rapid processing of things and things that rely on perception. So hearing, seeing tend to decline as we get older. So we know that processing music relies on hearing, perception, and we know that processing music involves thousands of notes potentially every minute. So our prediction would be older adults should do worse on music perception tasks. So we looked at this, and we looked at a few aspects. I'm going to talk about two today. We looked at two aspects of music perception. One is tonality. This is the relationship of notes to themselves, so like do, re, mi, fa, sol, la, ti, do. And we looked at rhythm. So this is how music unfolds over time, beats and meter and things like that. So first we looked at how the brain responds to bad notes. So we played a melody for a person, and the first melody is simple little melodies, and then we threw in some bad notes every so often that sound like this. We hear the sort of off note there, and we can worse. So what was amazing about this task, we asked people to detect the bad notes, and the older adults were better than younger adults in both situations. What was interesting, though, is we looked at their brain activity, and there's two responses that are typically associated with detecting bad notes in the brain. When you measured them at the locations we expected to see them, the activity seemed lower in the older adults, but it was more widespread, which suggests that during music perception tasks, like detecting a bad note, that there's some automatic plasticity that's occurring, that older adults seem to automatically reorganize their brains to maintain good music perception as they get older. We also looked at rhythm. So how do we do that? We played some rhythms for people and asked them to tap along. Quiet. That, we had a more complicated one. That's the task. And then we looked at the performance. Don't worry about the graphs. We looked at two different measurements here. One is accuracy, so how close they were to the beat. And the second is consistency. So were they always close to the beat, or were they tapping all over the place? And there was no difference between older and younger adults in this task. Both did it equally well. Then we looked at brain activity. And with brain activity, with rhythm is really neat. Your brain synchronizes with the rhythm. So if you have a beat going like this, you get a brain wave, boom, boom. So if there's a beat twice a second, 2 hertz, we get a brain wave at 2 hertz. And we can then measure those brain waves in response to the rhythm. And again, the amplitude of those, the strength of those responses to each of the frequencies in the rhythm was not different in older and younger adults. No difference. So what we can tell from here is music perception seems to be relatively preserved in older adults. And it suggests that the neural architecture that supports music perception could potentially be used as a cognitive scaffold to develop rehabilitation programs. And what do I mean by this? I'll use an example, something called melodic intonation therapy, and hopefully that'll make sense. Um, there's a group of people with a condition called aphasia, and aphasia makes it very difficult to speak. What's interesting is a subset of these people can sing, but they can't speak. And so melodic intonation therapy uses that. So they have an area of strength, which is singing, and an area of deficit, which is speaking, and they reteach people to speak by singing. So you start out by saying, hello, how are you today? And then slowly turn from singing into speech. And it works for some people. So they take that area of cognitive strength and use it to rehabilitate an area of cognitive weakness. And so we might be able to use music and musical features in sound as a way to help people learn to identify speech and noise better. And this is sort of something we're working on right now, as to ways to figure out how to do that. So to summarize, music training can be used to improve hearing abilities in older adults through the speech motor system. Music perception is stable in older adults. And as we work towards improving hearing in older adults and developing these music-based forms of auditory rehabilitation, we should focus on things like integrating the auditory motor systems, connecting music to speech in order to scaffold impaired speech perception with preserved music perception. Thanks very much. Thanks to all the lab members and funding sources. And I'd like to invite everybody up now, well, not everybody, but the 3 other speakers, and have a little round table. Thank you.